It's just looking at concavity and rates of change. And the second derivative measures concavity, which is how the first derivative changes. The greater the magnitude then of concavity, the faster the rate of change changes. There's a curve, there's the point P. So what's happening at that point P? We know that the derivative is positive because the slope's positive. We also know the concavity is negative. So that would be increasing at a decreasing rate. So it's increasing because velocity is positive, but at a decreasing rate because they're in opposite directions. So it must be slowing down. Whereas this one here is decreasing, but at an increasing rate because now velocity and acceleration are in the same direction. This case would be one where it's still decreasing, but now at a decreasing rate because now acceleration and velocity are in opposite directions. And the last case there would be the one where it's increasing at an increasing rate because they're in the same direction. So that's the same idea. A little graph there. Petrol consumption versus population density. And the question simply is, what can be concluded about petrol consumption as the population density increases? Well, if we look at the actual graph, the graph's always decreasing, so velocity is negative, but we're talking about a curve that's concave up. It's positive, they're in opposite directions, therefore petrol consumption is decreasing, but at a decreasing rate. Oh, how appropriate as we're in autumn at the moment. But how does the temperature change during autumn? So there's one of those climate graphs with maximum temperature and minimum temperature. And we can see that at the start of autumn, which is of course March, of course, is the beginning of autumn. But if you look at the graph at the beginning, then it's decreasing at an increasing rate. The slope of the graph is negative, but it's concave down, so they're in the same direction, decreasing at an increasing rate. In other words, it's saying, hey, it's getting colder, and it's getting colder quite quick. But then during autumn, it slows down. So if we look around May, we can see concavity has changed. It's still decreasing, but the concavity's changed, so now it's decreasing, but at a decreasing rate. It is still getting colder, but the rate of change is slowing down. All right, let's go back a few years then. On March the 22nd, the Prime Minister announced stage 1 shutdowns. I think that was the first one. What year was that? 2020? 21, 20, wasn't it? So what I did is I pulled out those, remember all those graphs they were putting up every day? So at the time I pulled out that graph and went, oh, well, let's have a look at it. Now they were saying at the time, may well have been true, that it takes about 5 to 6 days for symptoms to show. So the question is, looking at this graph, would you think the measure's been effective? So they announced it on the 22nd of March. 5 days later would be the 27th of March. And if we have a look at the cumulative curve, so the curve is the cumulative cases. These, of course, are all the new cases with the columns. And if you have a look at that, the curve's inflected. It's changed from concave up to concave down. That would seem to suggest that the measure was working, because whilst the cases were still increasing, but now it was at a decreasing rate. So back in those days, you remember how everyone was obsessed about the peak? Oh, when are we going to reach the peak? Well, mathematicians weren't. We were just looking for the inflection point, because we knew once the concavity changed, okay, we're on the right track. See, that's why maths is useful. Oh, there we go. Okay, so there's a little bit about that.